Hi, good morning, everybody. So, we started discussing statistics in the last lecture, and the book that we will be following is Introductory Statistics by Sheldon Ross, third edition. The other topic that we will do in the last, I think, 2 weeks is information theory, and the book that we will be following is Elements of Information Theory by Thomas and Cover, second edition. So, starting with chapter 7, we started with chapter 7 in the last lecture, distributions of sampling statistics. And we started with an example about a roulette table that if you were to bet $1 on a number and the options are 0, 0, 0, and then 1 through 36, then when you lose $1, and when you win $35. But the probabilities are different. For the loss, the probability is 37 by 38 because you could lose that many number of times. Winning probability is this. So basically, when you compute the expected value, it's in negative. So the intention is to uh, tell that it is an unfair game. It is not a fair game. We call a game as fair when the expected value of winning is zero. That is when we say a game is fair between two players A and B, when the expected amount of win is zero. Now, going forward, we will see exercises wherein we will see how to compute probability of winning if you place 100 such bets or 1000 such bets or 10,000 such bets. And the intention is to say that the longer you stay in the casino, the more you end up losing. It does not increase your odds of winning, it actually decreases your odds. Okay, then we define what is the sample. X1 to Xn are independent random variables having the common probability distribution. So this is important. They are independent and they have the common probability distribution. So if suppose you are so you can't have x1 say is the height of a person and x2 be his marks in midterm and x3 be the weight of the person. That does not work. They need to be independent, but they also need to have a common probability distribution. If you're talking about marks, you want to have all the variables about marks of the person in the exam. Then we define the sample mean, which is the mathematical average of all the values. Um, and the main point to be noted here is that x bar itself is a random variable. Why? Because x1, x2 up to xn, these are randomly chosen. Okay, if suppose you were to talk about average adult, average height of adult population, and you are taking a sample of 1,000 people, and that sample of 1,000 people will depend upon who is making the selection. So, for example, in this class, Aditya may make a different selection of 1,000 people in India to measure their height. Vidhi may make a different selection of people. Anand may make a different selection of people. So, different people may uh, different people may choose different samples. So, x1 to xn will differ each time we're doing the sampling, and x bar will differ. Why will x bar differ? Because x bar is a function of x1 to xn. So what we are saying is that x bar itself is a random variable. The point to note. X bar itself is a random variable. So then we can talk about its expected value and its variance. Okay, so its expected value turns out to be the population mean, and its variance turns out to be the population variance divided by the size of the sample space. How many things you are sampling. Uh, and again, the main point to note here is that variance goes down as sample size increases. We did the proof also towards the end, but this is the main crux of it, that variance goes down as the sample size increases. Yeah, so this is what we try to plot here. And what you notice is that for higher values of n, uh, the curve is narrower, and for lower values of n, the curve is more flattened out for n equal to 1, and this one is for n equal to 10. So it's more um, closer to the mean. So it's narrower. We then looked at some examples, sample of, so I'll skip this part. Basic idea is we wanted you to compute x bar and then variance. Uh, then we did it for sample of size 3. And then we did it for a sample wherein probabilities are not equal to half and half. One probability is 0.7 and the other probability is 0.3. Yeah, and here is a quick proof of what we said in the beginning. X bar is x1 plus x2 plus xn by n. So expected value of x bar is expected value of this item. Over here, we use the linearity of expectation. So expected value of ax plus b is a times expected value of x plus b. So we use that here. So it becomes 1 by n comes out, expected value of x1 plus expected value of x2 and so on. All these are equal to mu. So this becomes equal to mu. For variance, this b has no significance and a becomes a square. So this 1 by n becomes 1 by n square. And then you add it n times, so you get n here and n square here. So 1n cancels the 2, so sigma square by n. And that's where we stopped last time. Any questions about the last lecture? Okay, so I'm assuming that there are no questions. Let's move ahead to the next topic, which is the central limit theorem. So let x1, x2, xn be a sample from a population having a certain mean we have certain population with mean mu and standard deviation sigma. So, by the way, just note about notation. You want to be careful about the notation when you're working, when you're answering a question, because messing up the notation can make everything go wrong. So, whenever we use mu and sigma, we're talking about the population mean and population standard deviation. That is something that you want to keep in mind. Then for large values of n, and by large what we mean, let's say 30 or more, but sometimes even lesser value may work, but definitely more than 30 would work. Then for large values of n, the sum x1 plus x2 plus xn will approximately have normal distribution. With mean and mu and standard deviation sigma into root n. Okay, so it's a very powerful theorem because we are not making any assumption about xi. We are not saying that x1 to xn are normally distributed. We are not saying they are binomially distributed. We are not saying they have a Poisson distribution, hypergeometric distribution, geometric distribution. Uh, we are not saying anything about the distribution of x1 to xn. That is what makes this theorem so powerful. So x1 to xn could have any probability distribution whatsoever. Okay, so they are a sample from a population having a mean mu and a standard deviation sigma. Then what we are saying is that if you have enough number of random variables, then the sum x1 to xn will approximately have a normal distribution. Mean and mu and standard deviation sigma into root n. So that is the beauty and that is the power of this theorem, that no matter what the random variable be, you know, no matter what the underlying random variable be, the sum of these would have a approximately have a normal distribution. So let's see. Let's try to get some intuition into it. Um, so let's say you were to plot. Let's say you throw a dice, okay, and you may get one or two or three or four or five or six. These are possibilities. So this is your value of x. X. You throw a dice. You look at the output. You define that output to be x, and then you plot the frequency of getting x. You could call it frequency. You could call it probability. So you are throwing the dice many times, and then you're counting how many times did I get a 1. Let's say this is 1, 5, and 6. And now you're trying to plot. So let's say you get 1 many times, you get 2 a little bit less, you get 3 a little bit more, you get 4. This is how the plot would look like. If you have one dice and you throw it and you plot the number of times each output comes. Now, let's say we do the same experiment with 2 dice. Then how would the graph look like? Throw 2 dice. The first question is, what are the possible values that the sum could take? So dice 1, for example, output is x1, and dice 2 output is x2. And what you're doing is you're plotting the sum of x1 plus x2. So first question is, what are the possible values that x1 plus x2 can take? Is anybody
2
there?
to 12.
Oh, very good. Thanks. Somebody is there. Hemant Joshi. Okay. Yes. 2 to 12. And what is the? How often will you get 2?
One time.
What do you mean one time? In terms of frequency, or let's say in terms of probability, what is the probability of getting a 2 when you throw 2 dice?
1/36.
Yeah, because you need to get 1 on both the throws. So let's say it is somewhere over here. What is the probability of getting a 3?
2/36.
Double in height. What about 4?
3/36.
Will it keep increasing forever?
Up to 7.
And then what happens?
It will start decreasing in the similar manner.
Yeah, it will be symmetric. This is what you see. Now, how will it look like for 3 dice? If you were to throw 3 dice, then what will be the range of x1 plus x2 plus x3? Where will it start from and where will it end? Smallest and largest
3
value?
to 18. 3 to 18.
Yeah. And what would the graph look like? What is the probability of getting a 3?
1/216.
Yeah. That is for 3 and also for 18. And then it will keep increasing. And then it will start decreasing. And what you will see is if you were to keep doing this and you go up to about 10, 11 dice, this graph will start looking more and more like a normal distribution. You started off with a flat graph. This is for one random variable x. Then x1 plus x2. There is some shape which is coming up. Then x1 plus x2 plus x3, you're getting more shape. And then if you do it for 10 random variables, it will look more like normal distribution. You do it for like 30, you take 30 dice and you throw them together, and then you plot the sum of those 30 dice, then it will really, really look like a normal distribution. But what was the underlying distribution? What was the distribution of each xi? Was it normal? Was it binomial? Was it Poisson? What was it?
Hello, sir.
Yeah.
Sir, some students who are on campus was having some connectivity issues, so they are requesting to unlock the meeting.
Guys, this will go on. I cannot do it. I'm sorry.
Okay, sir.
I was very clear in the instructions, and for some reason, um, students don't want to follow instructions. That's all I can say. I'm sorry about this. By the way, next week, this time we might be meeting in an actual classroom. That is what I understood from the email from the dean last night. I thought our lectures are starting from the 18th, but the email seems to indicate that from the 1st April we'll have hybrid lectures. So we'll see how that goes. Okay, so continuing with our discussion. So, what is the distribution of each xi? We saw the distribution of sum of xi's, and we saw that it is tending towards normal. What was the underlying distribution?
Gaussian distribution. Uniform.
It's uniform. Correct. Great. And this is what we are. That is why we say that this is uh, such a powerful theorem. So x1 to xn, we are not making any assumption on the distribution of xi. It is a sample from some population having a mean and a standard deviation. So you could try this experiment with a population having a Poisson distribution or a binomial distribution or hypergeometric distribution, any distribution whatsoever. And I would encourage you to do that because it gives you a lot of confidence and it allows you to visualize how central limit theorem looks. In fact, there are many online simulators where you can put xi, you can choose the distribution of xi, you can say a value of n, let's say 5, 10, 15, 20, and then you can see as the value of n is increasing, then the sum of xi is starting to look more and more like a normal distribution. So it's a very powerful theorem. The intention of this example was to uh, give you some uh, visual intuition behind how it looks, not about the proof, but about the implication of this. Okay, so now let's see how it translates into mathematics. So let's look at an example. So insurance sector, we will have many examples, and the other sector. So the whole area, it started from gambling, probability, and statistics. The the source of this whole domain was gambling. People were gambling, and they wanted to know what are the odds of winning. Different kinds of gambling, but the basis is probability theory. But right now, one of the biggest applications is the insurance sector, and the other big application is essentially happened in the last few years is data science, because you have so much data. Uh, Google has a lot of data, Facebook has a lot of data, advertisers have data. When you do online shopping, you add to the data. When you browse, you add to the data. So there's a lot of data, and the corporations want to predict your behavior. They want to predict the next step that you will take based on that data. So it's called statistical inference, and that is the other big application of this area. So let's look at this example from the insurance sector. So an insurance company. So what does the insurance company want to do, by the way? I mean, for all of you, for all of us rather, insurance company has got a table that if you were born in this month of this year, uh, then this is the probability that you will die the next 1 year. It's as simple as that. It comes down to that. And based on that probability, they will tell you that if you take a life insurance, then the amount of money you need to pay every year so that we can make a profit. And then they do a similar thing for medical insurance, that this is the probability of you falling sick. They do the similar thing for vehicle insurance, motor vehicle insurance, that is the probability of you actually getting into an accident. So they have these huge tables which they have computed over the years. They have added a lot of data. So they have done a lot of statistics on data, and they have these tables which tell the probability of you getting into an accident if you are from a certain city, you have a certain age, you drive a certain kind of vehicle, you live in a certain locality within the city. They have all these data, and based on that, they tell you how much premium you need to pay. Okay, so an insurance company, let's say, has 10,000 automobile policy holders. If the expected yearly claim per policy holder is $260 with a standard deviation of $800, then approximate probability that the total yearly claim exceeds $2.8 million. So this is the kind of analysis that they are really interested in. So how do you get this number, expected yearly claim? So this is, they have computed it over the years, over the decades. Some insurance companies are more than 100 years old. So they have data. Based on that, they have said that, okay, on an average, a person spends about $260 per annum. But you also look at the standard deviation. The standard deviation is more than the mean, which is not usually the case. Standard deviation is really high. So on an average, a person is claiming $260, but the standard deviation is $800. Why would it be so high? So high because most of the people claim zero. Although the average is 260, most of the people, I mean, you all have motor vehicles in your house, most of the people claim zero. But then it's so high because some people get into a complete crash. Then they have to recover the cost of the whole vehicle. So average comes out to be this, but the standard deviation is really high. What this means is that most of the people are either claiming zero amount or close to full cost of the vehicle. That is why the spread is huge. $100 is a big spread. For a random variable whose mean is only 260. The mean was 10,000 and the standard deviation was 800. It would have made some sense, but this is more than three times the mean. So the standard deviation is more than three times the mean. So that tells you a lot about how uh, um, broadly distributed the claims are. Okay. Now, what is given to you is this, and you are given this, and then the insurance company wants to know what is the probability that the total yearly premium, total yearly claim exceeds this much amount. So if they figure out a probability for this, then what can they do? They can figure out how much to charge you premium. So this is the total amount of money that they will have to pay. They want to approximate this probability. Now, if they want to make a profit, they can say, okay, we want to collect at least, so this is the amount of claim we have to pay out. Then they know how many employees they have, what is the salary that we have to pay to them, and then we want to keep some profit. And let's say we want to get a premium which is about 5 million, so that we can make some profit, pay all the salaries, and settle all the claims. So this kind of analysis is very important. Now, how will central limit theorem help us out here? So the question does not say anything about a central limit theorem. It doesn't say anything, and this will also be a challenge for you when you are doing a problem in the exam or even otherwise after you graduate from college. Uh, then you won't have exams, but you will still have problems. So you look at a problem like this. How would you know you have to use central limit theorem here? So forget that part. Let's.
Since here there are 10,000, like the policyholders can be considered as test, like the
number of the n which we used.
Yes, perfect. Very good. Yes, so n is 10,000, which means that you have random variables x1, x2, all the way up to x 10,000. Yeah, perfect. And then what? After this, what is it that you're interested in? This is a great start. N is 10,000, so you go from x1 to xn. Each xi has a mean. So, in fact, if you were to just state the question here, each xi has a mean of $260, and the standard deviation of each xi is equal to $800. What is given to us? But what random variable are we interested in?
The sum of x1 to x 10,000.
Yes, exactly. So we are interested in sum of, we are interested in this x, which is summation of xi, I from 1 to 10,000. And this is where you see that you need to, so till this point you may not know that you have to use central limit theorem. Okay, so you start understanding the problem mathematically. You write down, okay, n is 10,000, you have random variables x1 to xn, this is given to you, and then this is the random variable that you are interested in. But when you look at this summation, that is your first hint that you need to use central limit theorem, because you are not given anything about the distribution of each random variable. You are not told anything here. You're not told that this xi, this $260, has it come from a Poisson distribution, binomial distribution, hypergeometric distribution? Nothing has been given to you. Okay, nothing at all. So you just know that there are some random variable with a certain mean, and they have a lot of random variables. They all have the same distribution, and they are all independent of each other. The probability of one person getting into an accident and another person getting into an accident, I mean, these two random variables are hopefully independent, unless there is a pile up, like one vehicle crashes and then 20 more vehicles crash into it one by one. But that doesn't really happen in India because you can't drive at very high speed, so it doesn't really happen. So we are going to assume that all of these xi are independent from each other. Probability of each person getting into an accident is really independent of each other. Now, so we need to work on this x.
Hello, sir.
What we Yeah,
Sir, how did we get n is equal to 10,000?
it is in the problem statement. An insurance company has 10,000 automobile policyholders.
Okay.
So now for this x, what do we know about this x? X is the sum of these, so that's something that we know. But we want to know mean of x and standard deviation of x. What is the mean of x? The mean of x is simply
260 times 10,000.
yeah. And standard deviation of x is we did this in the it's in the statement of the theorem. पर तुम लोग कुछ लिखते नहीं हो. You are using your hand only for typing, not for writing. So it is given here.
800 times root of 10,000.
Yeah. So sigma into root of n. So that is the standard deviation. So sigma in this case is 800 and then root of 10,000. So this is root of n into sigma. Okay. So we know mean of x, we know standard deviation of x. Now this is n mu. This is root n into sigma. So now what is the probability that you want to compute? Probability that we want to compute is that what is the probability that is x? So the total yearly claim is what we have called as x. So this total yearly claim is your x. This is your mu, and this is your sigma. So the question that we are asking is what is the probability that x exceeds $2.8 million? So the probability x more than 2.8 into 10 to the power 6. This is the probability that we are interested in. Now, the standard trick here is to convert both the sides of the inequality, basically convert this item into a standard normal variable. And you do that by subtracting the mean dividing by the standard deviation. So this becomes probability of x minus n mu by root n sigma greater than 2.8 into 10 to the power 6 minus n mu by root n into sigma. And this is equal to probability of, so this part is z, the standard normal variable, wherein on the right hand side of the inequality you plug in the values, you will get 2.5, 0.0062. So there is less than 1% likelihood that the total amount of claims that they need to settle is more than $2.8 million. So this probability is turns out to be 0.62%. So if they have, so it's a very low number, a very unlikely event. So they could probably assume that the total yearly claim is about $2.8 million, and based on this, they can do the other calculations and figure out how much premium to charge. They'll also have a good idea of how much profit they can make. Okay, so this what we said till now was about the sum of random variables. You take n number of random variables, you do the total. If you have enough number of random variables, then we are saying that their sum is a normal distribution, is approximately normal distribution for large values of n. Now we want to see the mean. What happens to the mean? So distribution of the sample mean. Sample mean is this. So what we know from the central limit theorem is that this item is normally distributed for large values of n. Now what we are doing to compute the sample mean is simply dividing it by a constant, or you could think of it as a multiplication by a constant. N is a constant. So it stands to reason that if summation of xi has normal distribution, summation of xi multiplied with a constant also has normal distribution. Okay, and then taking it further, we can say that x bar minus mu by sigma by root n has approximately standard normal distribution. Here also I should put approximately. So x bar has approximate normal distribution, and then x bar minus mu divided by its standard deviation sigma by root n also has approximate standard normal distribution. Okay, so just to reiterate, x bar is sample mean, n is sample size, mu is population mean, sigma is standard deviation of the population. So again, I'm reiterating, be very careful with the notations. X bar is this, mu is this. Don't mix them up. So now let's say we want to compute certain probability. Let's say you want to compute probability of X bar less than or equal to 8. For some reason, let's say we are interested in computing a number like this. So then this is equal to probability of X bar minus mu by sigma by root n less than or equal to A minus mu by sigma by 10. What we have done is on both the sides of the inequality, we have done a subtraction and we have done a division. And then we say that, okay, this first part is approximately standard normal. We get A minus mu by 10 over here. That is standard normal. So it is common to use that. In fact, almost a norm to use that to represent standard normal distribution. Okay. So how many of you are there right now? 70. Okay. So what I'm going to do is I'm going to give you an exercise and break you into smaller sections. So let's say you're measuring blood cholesterol level of people. Of employees in your organization, and you think that the population mean is 202, which is actually high. It should be less than 200, and the standard deviation is 14. Okay. Now you want to know this: if a sample of 36 workers is selected, approximate the probability that the sample mean X bar will lie between 198 to 206. Okay, so you are given the mean, you are given the standard deviation, and you take sample of 36 workers, and you want to approximate the probability that the sample mean will lie between 198 and 206. And then you repeat this 64 workers. Okay, so you try it out. I'll give you a few minutes to do it. Okay, so I hope you've noted it down. I'm putting you into breakout rooms. Try it out. We'll meet in about 8-9 minutes. For part A, what is the first step?
Hello, sir.
Yeah.
So here x bar is between 198 to 206. So we'll subtract mu and divide by sigma by root n.
Yeah. But before that, you want to just set it up and write it in the language that's. So I'm just writing it in detail so that you know how to write.
Yes.
So by central limit theorem, x bar is approximately normal. Okay, so expected value of x bar is equal to mu, which is 202, and standard deviation of x bar is equal to sigma by root n, which is 14 by root 36, 7 by 3. This is what we know. Okay, so then we take z is equal to x bar minus mu by sigma by root n, x bar minus 202 by 7 by 3. So this is approximately standard normal distribution. Okay. So what do we need to find? Probability of what? Probability of x bar lying in this range, 198 and 206. So probability of 198 less than or equal to x bar less than or equal to 6 is probability of 198 minus 202 by 7 by 3 less than or equal to x bar minus 202 by 7 by 3 less than or equal to 206 minus 202 by 7 by 3. So that is probability of minus and then you look up the tables, you get this to be 2.913. How many of you got this answer? Can you put it in chat if you got it? Vivek saying yes. Okay, great. Bihar. Okay, I see that. Mudit. Okay. Sarthak, Parth. Good to see some of you got it. Now, what about part B? Anybody got part B? What is the difference? In part B, so part B, the difference is in the standard deviation. What is the standard deviation in part B for x bar?
1.75.
Yeah,
7 by 4.
yes. Exactly. So then your standard normal variable in this case is this is approximately standard normal. So you have to compute and when you do that, then you get I'm assuming you're all comfortable with the standard normal distribution tables by now. You know how to look them up and all. So this is something that you will be doing a lot of in this half of the course. Normal distribution will be the most studied distribution that we'll work on. Okay, any questions about this example? Anything not clear? Any questions, doubts? Okay. Yeah, I think I lost track of time when you went on a breakout room and when you came back, I wasn't here. I'm sorry about that. I think I lost track of time. Okay. Let's do one more example. So let's say we are measuring distance to a star. The unit is light years. You're making 10 readings, and your population mean is the actual distance. And then the standard deviation of your readings is 3 light years. Your sigma. And this is your mu. Now you need to approximate the probability that the astronomers estimated value of the distance will be within half a light year. So you are measuring distance to a star. You are obviously measuring the distance in light years. You take 10 readings. The population mean is the actual distance d, which is unknown. If you knew d, why would you be taking the reading? The actual mean is unknown. You don't know what is the actual mean, but you assume it to be some number d, your mu. Standard deviation is 3 light years. Now you want to approximate the probability that the astronomer's estimated value of the distance will be within half light years. Within half light years of the actual distance, which you don't know. So, how will you work on this? So, it is obviously an application of central limit theorem. That is what we are doing. But how will you go about doing the problem? It is slightly different from the last problem in the sense that you're not given the population mean. You don't know the population mean here, just some number d. Yeah. What is it that you need to compute? How will you set up the problem? The maths will be easy. Doing, uh, for example, if you were to compare it calculus, uh, the, the calculation part in this course is pretty easy. The only challenge is setting up the problem. So what will be the first step? How will you write it? Yeah, what will be the first step? Are you guys still here?
Yes.
Yeah, there are 50 people here. Okay. Yeah. So, what is the first step? How do you start writing? How do you start solving? What is given to you? It is given to you that you have made 10 measurements. That is given to you. Let's start with that. So, you're making 10 measurements. Making 10 measurements. Then, you will estimate the distance based on these 10 measurements. How will you do that? You will take their mean. Yeah. Now, what is the expected value of this mean? What is the expected value of x bar? What is e of x bar?
Mu.
Yeah, and what is mu in this case?
D.
Actual distance.
Yes, perfect. And what is the standard deviation of x bar?
Sigma by
3 by root.
Sigma by root n. 3 by root 10. Right? Now, what is it that we want to compute in terms of x bar? What is the probability? We want to compute some probability. What is that probability that you want to compute?
X bar less than
X bar minus
0.5.
D
X bar minus d.
mod less than 0.5.
Perfect. That is what you want to say. That distance between difference between the mean and the actual value is less than or equal to 0.5. So that's what we'll do. So what we are saying is x bar minus t is less than 0.5 and greater than minus 0.5. Quality or equality doesn't matter. And now what do you know? You know that x bar minus t. So now if you divide both the sides by 3 by root 10, all the sides by 3 by root 10, then the term in the middle becomes standard normal. Yeah. So that becomes standard normal. So you get probability of minus 0.5 by 3 by root 10 less than or equal to z less than or equal to 0.5 by 3 by root 10. So this is probability of minus 0.527 less than or equal to z less than or equal to 0.527 turns out to be 0.402. So the probability is 40% that uh, the difference from the actual difference between the average and the actual distance is less than half a light year is 40%. Okay. So any questions in this example? Okay. So we'll stop here. I wish you all the best for shifting back to the campus, and those of you who have shifted back, welcome to the campus. This is probably the first time you're coming to your campus, and I really hope and pray that things go well from now onwards and the situation never arises again. and you are able to continue here for the next 2 years without any issues. Thank you guys and wish you all the best.